We've had our challenges in organizing this session, but I didn't know how difficult it was going to be until we lost Kurt on August 29th. Fortunately, we had Matt Laybourne has stepped up to the plate and is going to talk about advances in the use of isotopes in geochemical exploration. Matt has just joined Queen's University as an associate professor in geochemistry. He has a BSc from Kaiser University and MS and PhD degrees from Acadia and Ottawa, respectively. Worked in government at GSC and GNS, industry with ALS for a time, and academia at Texas, Laurentian, and now Queen's. His research and that of his students focuses on the geochemistry of fluids associated with ore deposits. They are specifically interested in the fluids that form various styles of mineralization, hypogene dispersion of elements into host rocks, supergene processes, and using modern fluids for mineral exploration. They use a variety of geochemical tools with an emphasis on trace metals, metalloids, stable and radiogenic and non-traditional isotopes. Matt Laybourne.
Thanks, Hugh. Yeah, step up to the plate. Usually if I do that, 3 strikes and I'm out, but I'll try my best. Okay, so just a couple of things before I get started. So yes, I had Kurt's paper. I don't actually know what he wanted to present, so I'm giving you a few thoughts of my own. I could talk all day just on isotopes related to VMS, so I'm just going to give a few snippets of some things that are quite interesting in a variety of different isotope types, and then get on to some sort of analytical advancements and so forth. Just a couple of things. So Kurt was the founder of CUFR, the Queen's Facility for Isotope Research, and it's one of the premier isotope labs, certainly in Canada and probably globally. I'm not really here to be an advertisement, but Dan Leighton Matthews and I are now running it, and Dan's running it. I'm helping Dan, and we wanted to just say that those of you who have used the lab in the past, the lab will carry on. The university's committed to making sure that the lab remains a success despite Kurt's absence. Right, forward. So just a couple of, I'm not going to go into a long exposition about Kurt Kaiser, but I did want to just say a couple of things about Kurt. An incredible man, incredible scientist. Some real highlights, I think, that stick out for me about Kurt. One was his ability to make people, and me in particular, feel like we actually knew something. It would have been so easy for him to just take the conversation away because the guy was brilliant. And the second thing is, I don't know how many of you have ever tried to put students into a lab to get them to do stuff, and I've done it in many places, and I don't know about you, James, but it's really hard. And at CUFR, the students want to be in there. We have a master's student. We had to kick her out of the lab to go write her thesis because she was in there, doing analyses while the whole thing with Kurt was playing out. So that's a remarkable achievement as well. He built the lab became a family, and that's rare. So that's what I wanted to say about Kurt. He was a very good friend and an extremely good mentor for me and for many, many people in this room, I'm sure. Okay, so very quickly, what's the deal with isotopes? So James just gave an excellent talk on single element anomalies, and that's perfect. So if you can find something that works, and in Nevada, gold is the best indicator of gold. But there are other cases where we need a bit more information, or we want to design an exploration model, or we might want to look at much bigger scale things. And so we can use isotopes everywhere from the core mantle boundary up to the atmosphere in exploration. Okay, so they haven't really been used very much in routine exploration. For that matter, neither has groundwater, despite some of our efforts. And traditionally, isotope use has been hampered by cost, perceptions, perhaps, on complications in sampling, certainly complications in prepping samples for analysis, and so on. And then how do you interpret the data? Different isotopes have multiple working hypotheses that can explain their variations, for example. And so there's been an underutilization of isotopes for industry. And one of the things that Kurt was passionate about was trying to change that mindset. And some of the things that are going to help, at least that's what we think, to change that mindset are real advances in analytical technology, and James has mentioned a couple of them, but really pushing detection limits, and also our ability to measure isotopes far more systematically and with far less sample preparation. Okay? And so then the challenge would then be to develop guidelines or cookbooks on, okay, you collect this isotope for this kind of mineralization, and this is how you might interpret the data, so that simplify the workflow so that you don't need to be a radiogenic isotope geochemist to understand what lead isotopes are going to tell you, say, in a groundwater. Okay, so how can isotopes, what do they need to be, right? So ideally you'd want it to be a definitive indicator of mineralization. It might be directly relatable, such as lead from a lead deposit, uranium from uranium mineralization, or it might be more indirect. Okay? And it may be more indirect but be highly useful for substantiating a process or a mechanism by which an anomaly might be expressed at surface, for example. Obviously, for isotope analyses, ideally, you don't want to be waiting for 6 months to get an oxygen isotope analysis from a lab because they can't get any bromine pentafluoride anymore. Well, right, you want something that happens very, very fast. Okay? You would like it to be able to relate the isotopic fractionation you see to your inferred processes for how metals are moving around. Okay? And then also, hopefully it's something that can become routinely measured by exploration. So a simple example would be lead. Lead is a very commonly included in just about any trace element ICPMS package. Well, why not just measure the different isotopes of lead? Then you have an isotopic composition, which may be very helpful, and I'll talk about that in a bit. So this is a quote from Kurt's paper. So the real power of isotopic compositions is that they elucidate specific processes that can be related to the mineralizing system and therefore have the potential to extend the footprint of deposits and identify false positives in element concentrations more effectively. Cool. All right, so what are we going to look at? Well, for isotopes, we can ignore the black ones because they're monoisotopic, right? So if someone comes with you a great research project for doing the isotopic composition of gold in groundwaters in Nevada, you can tell them no. Okay? Then we've got the red ones have 2 isotopes and the yellow ones have 3 or more. And you can see there's an awful lot of things on the periodic table there where we have potential to be useful in exploration. Just as a sort of an aside, a colleague of mine did this analysis for me. He went through the literature, and these are just papers over the last, sort of 25, 27 years, something like that, and the use of isotopes in studies related to mineral exploration. So not very many, but increasing. Okay, so what isotopes can we use? Well, we got 3 major, gotta get my fingers right here, 3 major classes of isotopes. We got the radiogenic isotopes, those that are produced by radioactive decay. We have the stable isotopes, ones that don't respond to radioactive decay. Of course, radiogenic isotopes become stable once they get to their end point. Right? And then what are called the non-traditional isotopes. One of these days we're going to have to get rid of that term because they're becoming a lot more traditional now. But sort of the metal, the transition metal and some of the metalloid isotopes. Okay? And so what do these tell you? Well, the thing about the radiogenic isotopes is that they don't fractionate by Earth surface processes. Or if they do, it's so vanishingly insignificant it's not important. And so they tell us a lot about source. So lead isotopes can pinpoint the source. And if you do it properly, they can tell you about time. How much time has taken for an anomaly to develop, or more specifically, what's the age of the mineralization that I'm looking for. The stable isotopes fractionate or change their ratios as a function of the source, temperature, redox processes, microbial processes. So these are isotopes that fractionate heavily at Earth's surface conditions. And finally, the non-traditional ones, again, can fractionate at Earth's surface conditions, and the extent to which they do so is actually very heavily dependent on redox. That is, how oxidizing or reducing the system. And so combining these things can tell us a lot about a system that we might be exploring for. So just go back to the periodic table here. So just very quickly, how do we measure these things? And this is an older slide, which I've modified. So we have gas source mass spectrometry, and this is the method of choice for doing most of the light-stable isotopes. Thermal ionization mass spectrometry, and this used to be the method of choice for doing the radiogenic isotopes. It's still used a lot because you can produce highly precise data, but its throughput is not as high as an ICPMS. And then, of course, multi-collector ICPMS, where basically you have a bunch of detectors so you can measure the isotopes simultaneously. That's great. Multi-collectors are pretty expensive, about $1 million a piece, so that's not so great. So as James mentioned, the quadruple ICPMSs can be used for many things. And so in the red boxes are things that could be measured either on a quadruple ICPMS or on a relatively new technology called a triple quad, which has actually only got 2 quadruples, but let's not split hairs, okay? And so what these instruments are opening up is the possibility to do isotope systems much more cheaply and more routinely, because these are the kinds of doing the same thing. These are the kinds of instruments that commercial labs like to buy because they're cheap. University labs like to try and convince government to get them those because they're expensive. All right, so we can use isotopes everywhere from the core mantle boundary up to the surface, and I'll give you one example of a core mantle boundary thing. But one of the big conundrums in exploration geochemistry, as James talked about, is seeing through cover. Right? We found a lot of the near surface or at the till bedrock interface deposits. And so how do we go even further? And one of the rate limiting steps in the success of exploration under cover is trying to understand how geochemical anomalies form at surface. Do they form? And if they do, what do they mean? How did they get there? And certainly elemental concentrations can help, but isotopes can be the sort of the icing on the cake that can really fingerprint a direct process. Okay, I'm not going to go through this all. It's in Kurt's paper, so you can read it there. But any number of ways of getting stuff from a deposit at depth up to surface. Okay, so why do we use isotopes? Because isotopes change, all right? So and this is called fractionation. And the extent to which they fractionate depends in large part on the mass difference, right? Which is along the x-axis here. Pardon me. That is the difference between the heavy and the light isotope in an isotope pair. So the mass difference for deuterium and hydrogen-1 is, of course, 100%, right? And as you go further higher in mass, the mass differences decrease. So when you get up to the heavy radiogenic isotopes, the mass differences are relatively small, right? And so on the y-axis here, we have the sort of kinds of fractionation that you might expect in nature in a measure of per mil. And all that per mil means is per thousand. We all know what percent is. That just means per 100, right? So per mil means per thousand. And what you can see is the red ones here are the light stable isotopes, and boron here as well. Sorry, getting myself lost here. And these ones can fractionate. They can show an extremely large fractionation effect because they're affected by things like temperature and redox state and biological mediation and so forth. And as you get heavier and heavier and those effects are less and less important, the extent of fractionation becomes smaller and smaller and smaller. But nevertheless, our instruments are now so sensitive that we can measure these fractionations. And in fact, combining isotopes that respond differently can tell you about a lot about a system. Okay, just a few examples. So this is from a paper by Bjorkman and coworkers, and really all it's showing is so this is part of the Abitibi Greenstone Belt, and this is the Marmion terrain. That's right. And so here's the geological map, and you can see on here there's a whole bunch of gold deposits and various other deposits here, and there's a recognized break here. Okay, but there's no structure evident over in here. Let's have a look at this map here. So this is a map of uranium lead age based on zircons. So they collect a bunch of zircons, measure the isotopic age, measuring uranium and lead isotopes, and then they've contoured it, right? And so the zircons represent things that can see through the surface down to what's happening in the deep crust. And essentially what it's showing is that we have this break in age right through here where we don't see any corresponding geological break necessarily, but there's clearly some kind of breakthrough here. And of course, most of the gold deposits in this area form along these structural breaks. So the power of this isotope system is that we're trying to image very large scale structures and perhaps opening up new areas of exploration. So now oxygen isotopes. Oxygen isotopes have been used for exploration for quite some time. And the traditional way of looking at it, this is sort of an example from various VMS deposits, but as you go into the core of the system, the oxygen isotope value decreases. Right? And well, just for reference, hydrogen isotopes tend to increase, and the details of why that happens is we can talk about offline. But so that's sort of the traditional thing. You're looking for a decrease in oxygen isotopes as a vector towards the core of a hydrothermal alteration zone. So this is a map of Isaac Lake, and from a paper that brain's gone, Taylor and Jan Peter and various other people put together, and they mapped the oxygen isotopes around this VMS deposit. And what's interesting is that, in fact, around mineralization, they have the highest isotope values. So in other words, more oxygen 18 than 16 relative to distal from the deposit. And what's really cool about that is because this deposit's been overturned, right? And so what you're seeing at surface is the more distal part of the hydrothermal system, the low temperature alteration, right? So it gives you this is a new tool for looking for deposits that might not be anything like in their original orientation. Okay. This is a really cool example of, so sulfur has 4 stable isotopes, 2 of which have been measured for a very long time, 32 and 34. So the other 2 isotopes, 33 and 36, are not measured commonly because it's difficult to do and most people haven't found a good reason to do it. So this is a study that Libby Sharman did and published a couple of years ago, looking at VMS deposits in this part of Quebec. My brain's gone here. And this is the Cap Delta 33 sulfur signal. That is the difference between sulfur 33 and sulfur 32. And there really shouldn't be much of a difference because the mass difference is so small. Okay? But this is plotted against selenium here and against gold content. And you know, these numbers in per mil don't look very big, but these are significant. And what these tell you is that the interesting thing about sulfur 33 is for Archean rocks, Archean systems, it can tell you that whether sulfur has seen the surface environment or not. Right? So in other words, the most magmatic sulfur, that is stuff that was added to the system by the magma that's feeding this system, has the highest gold contents and the highest selenium contents. Right? So direct implication of a magmatic hydrothermal fluid, and some of the sulfur in the system is from surrounding rocks that have been exposed at surface at some point in their existence. And this just follows up on that, but again, anybody's interested in this, I can send you the link. But so here we have the sulfur 30. Sorry, I got to get my head right. That's the 34 sulfur and the 33 sulfur, and showing a relationship between where you are in the system and how much magmatic versus how much seawater influence that system had. The more magmatic, the higher the gold contents. Okay? And unless you think that that's merely a trick of the Archean, here's some data from Brothers Seamount on the Kermadec Arc, where there's a VMS actively forming. And again, the sulfur isotopes vary as a function of gold concentration. Again, highlighting magmatic inputs into the system. So here we're using stable isotopes to try and understand process. And if we can understand process, then we can better develop exploration models and interpret how anomalies form. 1 minute. Oh my God. All right, lead isotopes. We'll skip through lead. lots of new instruments, going from 150K for a single quad, all the way up to $1 million for a multi-collector. Boy, I talked too long, don't I? Sample prep, there's a new way of chromatography is a laborious process for separating isotopes. You don't always need to do it, but if you do, it's a pain. There's a relatively new system called a prep fast, and again, I don't have time to go into this, but it basically automates chromatography. And so you can stick a whole bunch of samples in an autosampler, let it run overnight, come back the next day, and you've got a whole bunch of material ready to go onto your multi-collector or your triple quad or whatever it might be. Triple quad is a real, I think Jamil's going to talk about triple quads, so I'll skip that, but really potentially really exciting technology for doing isotope work, and in particular for laser ablation isotope work. Technique that's sort of pioneered in Kurt's lab was continuous flow ICPMS. That is, rather than doing a sequential or a partial leach in a variety of steps, you take your soil sample and you continuously leach acid, and it goes directly into the ICPMS. So you measure the entire thing through time. It can take 3 hours for an analysis, but what you end up is a series of curves, and what this shows you is where metals are coming out as a function of acid strength, which tells you where they've been sequestered in the soil sample, which is going to help you understand the anomaly better. Lead isotopes, you can do it for a few bucks now. It used to be hundreds, now it's a few tens of dollars to do a lead isotope analysis with enough precision and accuracy for routine exploration. And I will skip through that one, and my summary, and I'll go to that one because it's one of my favorite times with Kurt and with Dan was cruising down the Grand Canyon in a raft for 8 days. So I'll leave you with that and just say I really, really miss Kurt. Thanks.